Okay, it is a section 16.2, Convergence and Accuracy. A numerical method is said to be convergent if the solution of the finite difference scheme approaches the exact solution of the PDE as the grid spacing tends to 0. Let's define convergence in a formal way. A finite difference scheme approximating a PDE is convergent if this exact solution and approximate solution, the difference approaches 0 as the indicating point. Now approach to the continuous point, and now grid spacing is defined. So that is a formal definition of convergence. Let's see the difference between consistency and convergence. Consistency implies that the truncation error converges to 0 as the grid spacing is defined. Generally, convergence implies consistency, but the reverse is not always true. Okay, let's see here pizza delivery. Increasing the number of people involved in verifying the pizza order before delivery significantly increases the chances of correct pizza being delivered. Then it's a sort of a convergence can be achieved, and we can say at the moment the accuracy is good. Now the Ford-Euler scheme is convergent when this condition is satisfied. Mu delta t over delta x squared is bounded by 1/2. Let's try to prove this theorem. The error equation can be made in this way. Earlier, we considered, in fact, in the last section. Now we have this error equation, and now that is, here we have truncation error. Okay, for that one, we already know that the truncation error is order of delta t and order of delta x squared. We rewrite this one after multiplication of delta t and manipulate to get this equation. We assume this condition, mu is bounded by 1/2, which means that this is positive and this is non-negative, and also is positive. For convenience, we define these quantities. En is maximum of the errors at each grid point, and we take absolute value, and among them we try to get maximum value. So basically this is the maximum norm of the error on the nth level. And also same way for the truncation error, we try to define Tn, and for all Tn, now we take the maximum to get T hat. And also we have to notice that in the beginning there's no error because we'll use the given initial value. So here we have E0 must be 0. Now from this one we take, okay, now we defined some terms. We'll use those terms in our analysis. Okay, for this equation, now absolute value of this left hand side is bounded by, okay, this is positive and absolute value. This is non-negative, and then we can put here and absolute value this one, and then this one again here we have that it's quite easy mathematics for the absolute value. Now we are taking maximum to the right side over J, and we are taking maximum. Then now it'll become E n minus 1, and also it is the same because we are taking maximum, and from this one or that one the value will be the same, En minus 1, and of course from this one again En minus 1. And we have the maximum value of this one we defined here, that must be Tn minus 1. So we reach this one. Of course, this inequality, not equality, because we took maximum over the special direction. So we reach this one. Now, if we combine these three terms, then mu 1 minus 2 mu and mu, then the coefficient must be 1. So 1 of E n minus 1 and this one. So we reach this equation. Now we take maximum to the left-hand side. Then that will become, now this is independent on the grid points, so that we can take a maximum on the left-hand side. Then it will become En. So eventually we reach this inequality. Now we use this one recursively. Then En is bounded by En minus 1 and plus delta t Tn minus 1. That's exactly this one. Again, En minus 1 will be bounded by En minus 2 and one more term here, and so on. So that at the last moment, go down here in zeroth level, we reach here E0 plus that each level of transition error multiplied by delta t. But this one must be 0. So we have, right now, we have En is bounded by this summation. But now, rather than tk, we are choosing the maximum of this tk, which is t hat we defined here, and take this one, and then this summation can be delta t times n minus 1. That's exactly this one. And now n minus 1 delta t is always bounded by capital T, because we first partition in the time interval from 0 to capital T by n sub t, but n is anyway less than the n sub t, so that this one is always bounded by this value. So we reach at this one. So in any level, the maximum error, the maximum norm of the error is bounded by this quantity, which is order of delta t and order of delta x squared. So as delta t and delta x converges to 0, this value will go to 0. So that error is converged to 0, which means that the scheme is convergent when this condition is satisfied. Okay? The assumption mu is bounded by 1/2 makes coefficients in the Ford Euler scheme non-negative, which in turn makes Vj and weighted average of these values. Okay, that means that here, let's go to the earlier equation from the last section. Okay, let's see. Okay, here, once mu is bounded by 1/2, then this is positive this is non-negative, and then now that is here positive. So along with this source term, anyway, over there, these are a sort of average value for this new value. So we can see that this one is a sort of weighted average of earlier three values. Okay, so that's the comment we see here. Okay, now convergence analysis can often conclude in this way, so that the error, practical error, is order of the triangulation error, so that once we can see certain order of triangulation error, then we can prove in most cases the real error, numerical error, the same order, like that. The convergence analysis also called the accuracy analysis, because we are measuring, in a sense, accuracy. Here we have the difference between convergence and accuracy. Okay, a numerical scheme is considered convergent if its solution approaches the exact solution as the discretization method is defined. On the other hand, accuracy measures how close the numerical solution to the true solution. So accuracy is a sort of a measure. The convergence is a sort of a behavior, expressing some behavior. Showing convergence is not easy in general. So once we use, we try to here show the convergence for this simple problem, but once the problem is general or nonlinear problem, then the convergence proof is so hard, so that there is a related concept called stability that is easier to check. In computational terms, convergence is the property of numerical solution to approach the exact or true solution as the mesh is made finer. And we may consider some convergence along with archers. Archers can make more accurate shots through practice because they develop muscle memory, refine their technique, and become more comfortable with their equipment. So through practice, and you can be better. That is concept of accuracy improvement. And also, if you look at this one as some behavior, then it is a kind of a convergence toward the more accurate the status. Okay. Now let's try to solve the problem using the explicit time-stepping procedure, which means the Ford-Euler method. Okay, the same problem and same boundary condition. Now initial values are given in this way. For this problem, the exact solution is this one. So it's rapidly decreasing through the time marching, and e to the minus pi squared t. So as time increases, the solution value is really rapidly decreasing. Now for that one, and in special direction a to b, 0, 1, and capital T is 1, and this exact solution, that's u0 as the initial value, and we chose a 10 point in special direction, and so that we can get here dx, delta x, and grid can be made. Now, here from x0 to xn, so we have to get 11 points. So 10 subintervals. For these grid points, now initial value V0 is obtained. Okay. Now at 1, at the same grid, and from U, from definition, we can get exact solution at time is 1. We solve the problem for two different NT. One is 200, one is 170. For each one, we can get delta t and the corresponding mu, and we try to make Euler march from the initial value and mu and nt. We can get a v1, and that is the solution representing at time is 1. So we can measure the difference, the relative error, and print out. And also we'll try to get figure. Okay. Now for this one, Euler march, I implemented a different way here. There is the function. Okay. So exactly now for given mu times left side value, 1 minus 2 mu, the center value, and then now right value along with the mu is updated v. After updating for all the grid points, now that is the copied to v0, again keep going the iteration up to the last time. So that eventually v will be returned. Okay, so this is Euler march, and here we have results. When we are choosing NT200, then at the moment mu is 0.5, and earlier we proved that once mu is bounded by half, then the Ford Euler method is convergent. So that at the moment the L infinity, the maximum relative error is 0.15. So it's about 15% error. When we are choosing 170 points in time direction, then mu is larger than 0.5. It becomes 0.59. In the case, the relative error becomes 10 to the 6. For when now nt is 200, we have this solution. Now the black curve is for exact solution, and this one is for the Euler solution. Okay, look at this one. When nt is chosen such that mu is a little bit larger than 0.5, then solution becomes oscillatory, so that the algorithm scheme cannot control the solution. It's blowing up. So in a sense, the mu bounded by 0.5 is quite necessary, quite required. So consistency of numerical method is not enough to guarantee convergence of its solution to the exact solution. This for the Euler scheme is consistent. However, delta t is now a little bit larger than 0.5, then the numerical solution becomes here blowing up and oscillatory. From this example, we can see that now that's a kind of stability condition. We'll see the concept of stable condition in the next section. This condition is not only a sufficient condition, but also a necessary condition for the Euler method. For the Euler method, this must be satisfied. Without this condition, there's no guarantee to get a bounded solution. Okay, that's the end of the section. Thank you.